Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the PKI Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitaurus. Join the discussion. Join the PKI Consortium. Go to pkic.org/join.
Okay, I think we're good to go. It looks like we're up on the board. So for the next session, we're continuing down the sort of post-quantum firmware signing. And joining us today is Tan-Wai Kaey. She is an IoT and cybersecurity engineer with Panasonic. And she has strong academic foundations and professional certifications, including certified ethical hacking, Cisco CCNA, certified in cybersecurity. And her expertise includes obviously pen testing, vulnerability assessments, secure software design and development, and also obviously cryptography. So please join me in a big warm round of applause for Tan-Wai Kaey.
Yes. Right. Good afternoon, everyone. I'm Tan-Wai Kaey. You can call me KC. Right. So I'm an IoT and cybersecurity engineer, mostly focusing on IoT. Right. So today we'll be looking into the practical implementation of firmware signing in ESP32-based IoT devices. So, we'll basically look at how post-quantum signature algorithms such as the ML-DSA, which is what we'll be using today, can be integrated into the ESP32 secure boot process. This is to replace the traditional classical RSA or ECDSA signing that is in use right now. Right. So the goal is to make sure that the firmware signing process is fully quantum safe, but we have to keep it compatible with the current process that the manufacturers are using right now. So today we'll go into how we build, sign, and verify the firmware using Open Quantum Safe OQS library. So just to look over what I'll be going through. So the first one is the key IoT constraints. So the constraints are what are the limitations currently and how we can fix them using different designs. And after that, we'll go into the integration architecture on how PQC fits into the firmware signing and also the verification. Right. Next is the bootloader verification and the hybrid signing logic. And finally, we'll close with a simple roadmap where we can migrate from classical to PQC algorithms. Right. So when we're working with IoT devices, there are three main constraints we need to address. Right. So first is the classical algorithms like RSA, ECDSA. These are no longer future-proof. So once quantum computers become practical in the market, these algorithms can be broken, and it will expose all the long-lived IoT devices in the market, and firmware forgery attacks can happen. So, for example, an attacker can sign their own malicious firmware, and the device will just accept it with no questions. So, secondly, any new signing algorithm must always be compatible with the existing OTA infrastructure. OTA stands for over-the-air. Right? So we can't afford to break the current update pipeline that the manufacturers and users are already relying on, that they're already used to. And third, most obviously, IoT devices have limited flash size, RAM, and also CPU performance. Right. So even if PQC algorithms are secure, they must also fit with these constraints without extending boot time too much or like consuming excessive memory. Like for example, ML-DSA signatures are obviously larger than ECDSA. But on like modern microcontrollers like the ESP32, this difference is still manageable, especially when we optimize it at the compile time. So let's look at how PQC is integrated into the firmware signing and the verification flow. So this flow has two main components, the host side and the ESP32 side. So on the host side, once the firmware is built using ESP-IDF, then a custom Python script can be triggered. This script will use the OQS Python bindings to generate an ML-DSA signature to compile firmware. And the public key and the signature file are then inserted into the firmware header, alongside with the metadata such as the build date, algorithm type, or the version. Right, once that's done, the signed image is deployed into the OTA server, just like a normal update. So for the ESP32 side, the bootloader will be modified to recognize PQC signatures in the firmware header. When the device boots, it reads the firmware header to determine which algorithm will be used. So it can be classical, can be PQC. So if PQC is specified there, the bootloader will use the OQS C library that we're going to show later. Compile. So then the PQC signature verification will be done using the library. Right, so in the case that verification fails, the bootloader should safely roll back to the previous valid image. So this approach uses same secure boot flow as a normal one, but we extend it with the quantum resilience. Right, but this is done without any hardware modification. So inside of the bootloader, the verification logic is rewritten to use this OQSC API. Normally in the ESP32, we'll be using ECDSA function check. So we'll be replacing that with this function from the OQS library. So this verification function is It basically takes in the firmware data, the public key, and the signature, and validates it. Right, this is done using ML-DSA in this scenario. Right, so if everything is okay, the device will continue to boot the firmware. But if it fails, like I said just now, it will roll back to the previous partition. So as you can see, this is a demo of how the firmware is generated, signed, and verified using the ML-DSA. So the first picture, you can see the signing process where the firmware binary is filled and then signed. This is using ML-DSA through, like I said, the OQS library. And the public key and the signature are both embedded into the firmware header, just like what I mentioned in the architecture flow just now. Right. So at the middle there, we have the verification process, which is run on the bootloader itself. Right. So if there's any tampering or corrupted firmware, which is shown at the right-hand side bottom box here, the verification will fail, and of course the firmware won't be accepted, right? So it will roll back to the previous valid image. Right, so next up we have the hybrid signing. Hybrid signing means that we are using both classical and PQC together. Right. So this is very important in transitioning from classical into post-quantum algorithms, because it's not feasible to just do that overnight. Right? So this is an example of the header layout. It will be extended to fit both the ECDSA signature and the ML-DSA signature in. And then the bootloader can operate in two modes. So in strict mode, both of the signatures must pass the verification. So this can make sure that the firmware is trusted under both the classical one and the post-quantum algorithm. Right. So for compatibility mode, it will be either one passing will be sufficient. So this will help with a more gradual rollout for making sure that the older devices are still compatible and the new devices can verify using PQC. So the hybrid cryptography, it ensures that the current and the future systems are still using the same firmware. So there is also two different kinds of hybrid signing, nested and parallel. So in parallel signing, a parallel hybrid, parallel means that both the ECDSA and ML-DSA are verified parallelly, and the other one, which is the nested hybrid signing, which means that the either ML-DSA covers ECDSA or the other way around, and which means that both of them have to be verified successfully for the firmware to be booted. So that's parallel and nested hybrid signing. So the idea of the nested or strict mode is to make sure that if either one fails, like the classical is compromised or the PQC one is compromised, the firmware is still safe. So this is important in scenarios like ICS, industrial control systems, or more critical infrastructures. But of course, the parallel and the compatibility mode is easier to deploy, and it also fits with what NIST and ETSI recommends. So for now. So finally, we are at the migration roadmap. So this is a very simple one. The first is the hybrid signing transition. So this is to make sure that new and old devices can still verify updates securely. So if in the case that more devices in the market are able to support PQC only signing, right? So we'll aim to move fully to PQC signatures. So lastly, of course, we want to extend PQC integration beyond firmware signing into like TRS and also device authentication, so that the entire device lifecycle from boot to communication to cloud, it will all be post-quantum ready. So this roadmap can allow organizations do the transition gradually, making sure that the environment is still operational during the transition. That's all from me. Thank you.
Excellent, thank you. Any audience questions? Yes, there's one in the back there on the left, Harold.
So when you explain that you support